Okay, I picked again this problem because I thought the picture looked cool. And to be honest, I read this thing about 10 times. I could not figure out what it was saying. And after the 10th time, I finally figured it out. So this is what's going on. This is uh, an electric switch, like a solenoid. I don't know if you know, you can't really, you don't have the force to start your car. And so when you turn the ignition on, it turns on this electric coil, and if you'll take physics too, you learn about this, and it'll pull this thing back to start your car. It's called a solenoid. Anyway, what's happening here is you have this pretty stout spring on one side, and it's keeping that switch, I guess, what would you say, open, not you're completing a circuit or something like that. Anyway, it's contacting at A. And then you turn on this solenoid, and it has a magnetic force that will pull that blue arm flat horizontal. And so this magnetic force here bring this down. And what you want to know is how strong does that magnetic force have to be so that you can pull it down. Well, you want to make sure that that blue thing is securely up, that it doesn't just randomly come down, because it needs to stay up against A. And so what they tell you is that you design that spring so that it is holding that thing up very securely with zero point 0.4 newtons. Now, it's not that much of a force. Remember, an apple weighs about a newton. But, we're talking about a tiny little switch here. Anyway, there's a positive contact force there, definite contact force there of 0.4 newtons. And that's this free body diagram here. The first thing it wants to know is what's the force in the spring to make that thing stay contacted up there with 0.4 newtons. And we'll do that here. Then it wants to know how much do you have to pull down with that magnet, okay, RE, to make it come away from the contact. Now, what makes this a little funny is that when you pull that blue piece from inclined down to flat, can you see, it's hard to see from this picture, but when you pull down the right side, point C, it goes up. And in fact, it tells you it's 10 degrees. So if it's 30 millimeters from B to C, and that's 10 degrees, point C has to go up 5.21 millimeters. Okay, that's 10 degrees. So again, if that horizontal distance is 30 millimeters, it's going to go up 5.21 millimeters. Why do we need to know that? Well, the spring force is not constant. We calculated that spring force in part A, but we're going to stretch that spring an extra 5.21 millimeters, which means we're going to increase when it's horizontal, the force in the spring is slightly higher. Okay, so what we're going to do is we're going to solve part A first to get the force in the spring when it's inclined. We're going to use this geometry to figure out what the additional force is and the final force is when it's horizontal. And then we can tell you what the force in the magnet has to be to pull down. Okay, from part A, looking at free body diagram A, I'm going to take moments about B to get the force in the spring. You have the 0.4 newtons at that contact. Oh man, I guess I don't have those distances right. It should be 0.4 times 100 times cosine 10 degrees is the x component. Okay, and then you have that force of the spring. It's going clockwise, so negative times 30 cosine 10 degrees, and I lucked out, equals 0. The cosine 10 degrees cancel out. Actually, I didn't luck out. I knew that would happen, but I'm pretending that I got it wrong. Well, I did get it wrong, but I sort of in my mind knew that everything would stay proportional and cancel out. Anyway, it doesn't matter. You can keep that cosine 10 in there on both terms or cancel it out. You'll get that the force in the spring is 1 1/3 newtons when it's contacting at A. So when you are contacting at A with 0.4 newtons, on the other side, that spring is pulling at 1.33 newtons because it has a shorter moment arm. Okay, in part B, when the spring is horizontal, we went over that. It stretches an additional 5.21 millimeters, and they give us the spring constant as 120 newtons per meter. Well, you got to change that millimeters, 5.21 into meters, so it's 0.00521 meters. You get an additional 0.6 newtons. Starting with 1.33, which we got in part A, you stretch it down with another 0.625. You end up with 1.958 newtons in the spring. Now we just look at free body diagram B. Take moments about B again. And you have RE. Now these distances are definitely horizontal, so we know that's 50 from B to E, and we know it's 30 from B to C. So you have RE times 50 minus this new spring force, which is 1.958 newtons, times its distance, 30. That's going clockwise, so negative, and you get the solenoid, or the magnet has to pull down with 1.18 newtons.